Welcome to Creative World. In this video, we will learn about modular multi-level converters, how they work and why we use. In this video, we will also implement 7-level modular multi-level converter in MATLAB simulation environment. So without wasting time, let's proceed towards the topic of the video. First of all, what is MMC? MMC stands for Modular Multilevel Converter. We will learn about this type of converter through its name. As the name suggests, Modular Multilevel Converter. Its name is divided in three parts: modular, multilevel and converter. So modular stands for numerous identical individually controllable submodules. It means this type of converter will have multiple identical submodules which will have their own individual control. Second word, multilevel, indicates that the output of this converter will have multiple steps or multiple levels. And third word, converter, indicates that this converter is utilized to convert DC into AC. So for now, we just have to keep remember the meanings of these three words. In upcoming part of the video, we will deeply learn about these three terms: modular, multilevel and converter. Next, a question may arise: why we use MMCs? To answer this question, I have given some prominent reasons, but there are many more reasons to use MMCs. First reason is these are the latest type of converters which convert DC into AC in more efficient way. If we focus on two-level conventional inverter which converts DC into AC, it have only two levels. One is positive VDC and other one is negative VDC. Here VDC is the required output AC peak voltage. But on the other hand side, modular multi-level converters have multiple step voltage at their output waveform. Now, if we focus on these two waveforms, the output of modular multi-level converter resembles to sine wave. Output waveform of MMC is more close to sine wave rather than conventional two-level converter. So the first reason of using MMC is that these converters more efficiently convert DC into AC. The output waveform of these converters have low harmonics and more close to pure sine wave. Second point is a high voltage AC waveform could be generated with low voltage DC components. In order to justify this statement, we will again focus on these two waveforms. First, look at this conventional two-level square wave inverter. If we focus only positive half cycle of the output wave diagram, during this cycle, the electronic switches which are in open state will be bearing across them VDC voltage, which is the maximum required voltage of this inverter. These voltages are very high because it is the maximum output voltage which are required to invert. During this positive cycle, the electronic switches which will be in open state will be bearing across them VDC voltage. We can learn it through circuit diagram. Now if we see in this state, let's assume this is the positive half cycle. During this half cycle of the output wave diagram, this voltage which is equal to VDC will be appearing across this open switch as well as this open switch. Now imagine if this VDC voltage are in the range of kilovolts. So during positive half cycle in this state, whenever these two switches are in open state, during this stage thousands of voltage will be appearing across these open switches which can cause damage. On the other hand side, in modular multi-level converter, we will see in upcoming part of the video, A specific level of voltage appear across all electronic components, which is defined by the step voltage of this converter. No matter what is the value of voltage VDC, either it is in kilovolts, same voltage will be appearing across each module. So in this way, the electronic components used inside these identical modules will bear low voltage across them. So in this way, we can use low voltage level DC components inside these converters and generate very high voltage at output. These converters allow reliable operation of electronic components due to low level of voltage across these components. Now we will move towards the third reason of using MMCs. So third reason of using MMCs is a high voltage and high power could be produced without using bulky transformers. As we have discussed in previous step, in case of conventional two-level inverters, high voltage appear across electronic switches. So this is the limitation of conventional inverters. We cannot use those inverters to generate high voltage in AC. So what we do, we use these inverters to convert low voltage DC signals into low voltage AC signals. After this, we add transformers in front of these inverters to convert low voltage into high voltage. In this way, we have to use very bulky and large power transformers in front of these inverters. While in case of modular multi-level converters, we don't have to use any transformer. We can generate any desired output voltage by simply adding the number of submodules inside these inverters. So by increasing the number of submodules, we can generate very high voltage without using transformers. Move towards the next reason. These type of converters allow scalability. By increasing the number of modules, more precise sine wave could be generated. In previous step, we discussed by increasing the number of submodules, we can increase output voltage of these converters. Another benefit of increasing the number of modules is that we can get output waveform which is very close to pure sine wave. Here is a modular multilevel converter output waveform. Let's suppose the average of first step is this point. Similarly, average of second step is this point, and so on. Now if we join all these points together, you may see that we are getting average voltage very close to sine wave. Now if we decrease this step size and increase the number of levels, we will be very close to pure sine wave. And it is very easy in case of modular multi-level converters. It allows user to add up to their desired level of submodules in it. And by increasing the number of submodules, we will be very close to pure sine wave. And this is our main desired point, to get very pure sine wave at the output of converter. Now one thing to keep remember is that n is always an odd number. So what is n? N is the number of levels which are present in the output of MMC converter. So number of levels in any MMC converter is always odd. Now you will be thinking about, we have used word submodule a lot of time. What is basically this word? So now we will elaborate submodule. Before that, we have to discuss different types of topologies used in MMC circuits. There are a lot of topologies. Using these topologies, MMC circuits could be developed but we will focus only two well-renewed topologies which are used to develop submodules of MMC converters. These submodule configurations are: first one is half-bridge and second one is full-bridge. Half-bridge is basically two-level MMC converter which allows two level of voltage. First one is 0 volt and second one is VC, the voltage across capacitor. So we will learn about this topology with the help of this diagram. Basically this is the submodule of MMC converter in half bridge configuration. So let's discuss about this configuration. Let's assume voltage VC is appearing across this capacitor which is initially charged. Now there could be two options to get voltage across these terminals. First option is to open this switch and close this switch. In this case, this switch will be short circuited and zero voltage will be appearing across these 2 points, which is the first level of this half bridge. In second case, if this switch is open and this switch is closed, in this way the voltage across this capacitor will be appearing through this channel across these 2 points. So we can say that the second level of voltage across these points will be equal to voltage across this capacitor VC. So using half bridge configuration, we can get two levels of voltage across a single module of MMC converter. One voltage level is 0 and other one is the voltage value across the capacitor. Another point to keep remember related to half bridge configuration is that out of these two switches, one switch actives at a time. It means if this switch is active, in that case this switch should be opened, and whenever this switch is active, this switch should be opened. This is the very essential point of this configuration. Now move towards full bridge configuration. This configuration offers three voltage levels. First one is 0, second one is positive VC, and third one is negative VC. These VCs are basically voltage across capacitor. So now we will see how this configuration offers three voltage levels. Now this configuration have four switches. The switches in cross are linked together. It means S3 and S2 will be linked together, while S4 and S1 will be linked together. Whenever S1 will active, S4 will also be active. And one more thing to keep remember is that at a time only two switches are active while remaining two are deactive. Now I am assuming S1 is active, it means S1 is short circuited and S4 should also be short circuited. These two switches are opened. So how the output voltage will be retrieved? Here positive VC is appearing. So using this path, positive VC is appearing across this A point and negative VC is appearing through this path on point B. In this case we are getting positive VC. So this is the first voltage level retrieved from this full bridge configuration. Now imagine these two switches are opened while other two switches are closed. So these two switches are closed. In this case the path will be completed using this way. At this point B, positive VC is appearing, while on point A negative VC is appearing. Now in this case we are getting negative VC with respect of this polarity, because on positive we are getting negative voltage and on negative we are getting positive voltage. So this is the second voltage level which is retrieved from full bridge configuration. Now the third level is very easy. If all switches are opened, there will be no voltage across these 2 points A and B. So 0 voltage will be appearing across these 2 points, which is the third voltage level of this full bridge configuration. Now we will see the practical implementation of half bridge submodule configuration. As we discussed in the lecture, at a time only one switch active while the other switch is deactive. In this case, I have used these SPST switches in place of IGBTs. These are working same like IGBTs. Switch close mean IGBT is active while switch open is electronic switch IGBT is in open state or deactive. Now if we focus the first state whenever this switch is closed, in this case we are getting 0 voltage across these 2 points, which can be confirmed using this multimeter. Right now we are getting 12 picovolt, which is almost equal to 0 volt. Whenever I will swap the position of these switches, this switch will be opened and this switch will be closed. Voltage across this capacitor will be appearing across these 2 points, which is the output voltage terminals. So as we discussed earlier, in case of half bridge configuration, we get only two voltage level. First one is 0 and other one is voltage across capacitor. In this case, voltage across this capacitor is 12 volt because it is charged through 12 volt battery. So there should be 12 volt across these 2 points. You may see that I have swapped the positions of these two switches. This switch is active now and this switch is deactive now. Now we are getting VC across these two terminals, which are output terminals. Once more we will change the status of switches. In this case we are getting 0 volt, 12 picovolt, while in case of the active of S1 we will be getting 12 volt. So it is confirmed in case of half bridge configuration we get only two voltage level. First one is 0 volt and second one is voltage across capacitor. Those voltage will be appearing across output terminals of that module. Now this is the single sub module of half bridge configuration. We can connect these modules in cascade form to get multiple level of voltage. We will see this in upcoming part of the video. Now we will see the operation of full bridge configuration. In this case, this capacitor is charged through 10 volt source and these four switches are placed in place of IGBTs. Now as we discussed in lecture, at a time only two corresponding in cross configuration switches are active while other two remain inactive. At this state we are getting minus 10 volt. This 10 volt is basically the voltage across capacitor, but in this configuration whenever switch 4 and switch 2 are active, in this case we will be getting minus 10 volt. So this is the first voltage level which we get from full bridge configuration. Now I am swapping the position of switches and you may see that we will be getting positive 10 volt, which is the second voltage level offered through this full bridge configuration. Now in order to get 0 volt, which is the third voltage level offered through this configuration, we have to open these switches as well. You may see that we are getting third voltage level, which is 0.568, so it is almost 0 volt. So both configurations are validated through simulation as well. In case of half bridge configuration we get only two voltage levels, 0 volt and positive VC, while in case of full bridge configuration we get three level of voltages, 0, plus VC and minus VC, by swapping the positions of switches. Up to this point we have learned and implemented both configurations, but we will follow up half bridge configuration for the further part of the video. Now we will use this half bridge configuration to build three level voltage. So as we discussed earlier, in order to add the voltage levels we have to add submodules of this configuration in cascaded form. You may see here this is the single module of this half bridge configuration in which two switches are connected in series to a capacitor, and we know that these two switches are reciprocal to each other. If one switch is active, the other one should be deactive, and vice versa. And in order to add voltage level, first we were getting two voltage level from a single submodule. One was 0 and other one was VC. Now we want three level of voltage, so we will add another module in series of the previous one. In this case, this switch is closed, so its reciprocal switch will be opened, and this switch is opened, so its reciprocal switch will be closed. Now the path for output voltage will be formed using this direction. And one thing to keep remember, at this stage this C1 is charged at 10 volt, positive here and negative here, 10 volt. So in this case we will be getting 10 volt across these 2 points in positive direction, because positive voltage is appearing across this point and negative VC is appearing across this point. So here it should be 10 volt. Okay, move towards second case. In this case, this switch is remained closed, so its reciprocal switch will be opened, and now this switch is closed while this switch is opened. So voltage path will be, so in this case these 2 points are short circuited together, so there will be no voltage at output. So here it should be 0 volt rather than 10, it will be 0 volt. Okay, so up to this point we have retrieved two voltage levels, one is 10 volt and other one is 0 volt. Move toward the third level of voltage. In this case this switch is opened, this switch is also opened, so current path for this output voltage will be, inside this path two voltage are appearing, positive negative 10 volt here and positive and negative 10 volt here. So these two voltages are added together because these are connected in series connection. So output voltage will be 20 volt, the sum of these two individual voltages. So in this way you can see that by adding a submodule into previous one we get three level of voltages, and if we add the number of these series connected submodules, the voltage levels will be increased. Now we will see the simulation of this three level voltage converter. First stage, whenever these two switches are closed and their reciprocal switches are open, in this case these 2 points are short circuited and we are getting 0 volt, 19.999 picovolt, which is almost equal to 0 volt. Now I will swap the position of these two switches and we will see the first voltage level which is appearing across this C1 will be appearing across these 2 points. You may see here we are getting 10 volt which is appearing across this C1 as well as appearing across these 2 points. So first level was 0 volt, second level is 10 volt, and in third level we have to swap the positions of these two switches and we will be getting 20 volt. Here you may see that we are getting 20 volt. So using this configuration we got three voltage levels, 0, 10 and 20 volt. Now we will move towards 4 level half bridge configuration of MMC converters. As we discussed earlier, in order to increase the number of output voltage levels, we have to add the number of submodules in cascaded form. So one half bridge configuration module was giving 2 level of voltage. In order to get 3 level of voltage, we have to add another module cascaded form into the previous one, and in order to get 4 level of voltage at output, we have to add another cascaded module in the previous configuration. Now we will justify 4 levels of voltage using this half bridge configuration of cascaded 3 modules. In first condition, these 3 switches are closed while their reciprocal switches are opened. In this case, we will be getting 0 volt. How? Because through this path, these output points are being short circuited. Move to next state. In this state, only this switch is opened while other 2 switches are closed. So now this path will be formed for the current to flow. In this case, we are getting a voltage level 10 volt which is appearing across this C2. This C2 is being charged through this 10 volt battery. In this path, only one capacitor exists, so 10 volt across this capacitor will be appearing at output. Now we have confirmed 0 volt, the first level, second is 10 volt, second voltage level. Move towards third level. Now in this case, this switch is opened and this switch is closed. So the path will be formed. At this stage, we are getting 2 capacitors connected in series connection, so their voltage will be added together. Sum of these 2 capacitor voltages will be appearing across these terminals 20 volt because both of these are connected across 10 volt source. Move towards the fourth level of voltage. In this case, this switch is also opened, so path will be formed using this way. So using this way, we are getting 30 volt because 3 capacitors are connected in series and each of these capacitors are charged at 10 volt. So their sum of voltage will be equal to output voltage. So in this way, we are getting 4 voltage levels 0 volt, 10 volt, 20 volt and 30 volt by adding number of modules in cascaded position. Another point to notice is that as we discussed earlier in this video that in case of MMC converters, low voltage appear across electronic switches and it can be confirmed that the voltage across individual capacitor will be appearing across open switches. So as compared to conventional inverters, in these type of inverters, voltage across electronic switches are very low. So in this way, these switches can reliably operate for long time. Now we will see the simulation of this 4-level MMC converter in half-bridge configuration. First of all, we will swap the position of these 2 switches. Right now we are getting 0 volt. Okay. Now we have swapped the position of these switches and we are getting 10 volt. So 0 volt and 10 volt are confirmed. You may see after swapping the position of these 2 switches, we are getting 20 volt. 0 volt is first voltage level, 10 volt is second voltage level and 20 volt is third voltage level. Last one is 30 volt, which is the fourth voltage level by swapping the position of these 2 switches. So far now we have discussed and simulated up to 4-level modular multi-level converters using half-bridge configuration. Now we will try to develop the methodology for the implementation of 7-level MMC converter using half-bridge configuration. As we discussed earlier, if we want to increase the number of voltage levels, we have to add sub-modules in cascaded form. And here the meaning of 7-level voltage output waveform is 3 level is in positive direction, positive voltage, and 3 levels in negative direction, negative voltage, and 1 level is at 0 voltage. So here is the general block diagram of half bridge configuration if we want to develop an n level of MMC converter, we have to follow this generic block diagram. In this block diagram, this upper arm is responsible for the positive cycle of the output waveform, and this lower arm is responsible for the negative cycle of the output waveform. These two arms are connected together through inductors. These inductors are used to limitize currents in case of any fault. Now we will be getting voltage across these 2 points, which will be AC voltage in both directions, bidirectional output waveform. As we discussed earlier, in order to get 7 level of half bridge MMC converter, we have to use 3 submodules in upper arm and 3 submodules in lower arm. So total will be 3 and 3 6 voltage levels, and 1 voltage level will be 0. So we will be getting total 7 voltage levels. Now we will move towards MATLAB simulation and see the implementation of this 7 level half bridge configuration MMC converter. So here is the simulation file developed in MATLAB environment. First of all, this block is responsible to turn on and off all these IGBTs individually. Now if we focus on a single submodule, we have 2 IGBTs connected in series connection, and these are connected parallel to a capacitor which is initially charged at 5 voltage. All of these capacitors are initially charged at 5 voltage. Now in order to make reciprocal of these two switches to each other, we have added a NOT gate in series to the gate signal of a single IGBT. In this case, whenever this signal will be high, this gate signal will be low because NOT operation will be applied, and whenever this will be low, so it will be high. So in this way, these two IGBTs will act as reciprocal to each other. These 3 modules are forming the upper arm of MMC converter, while these 3 modules are forming the lower arm of MMC converter, and these both arms are connected to each other through these inductors. Here a load resistor is connected between these 2 arms, and we are measuring voltage across this resistance. These 2 blocks are used for the zero detection. These will detect the transition from positive cycle to negative cycle and vice versa. Now we will simulate the simulation and we will see the results. You may see here we are getting multi-level voltage output across load resistor in the form of AC signal, and we can also confirm the voltage level. We can start counting from here: first, second, third, fourth, fifth, sixth and seventh. So it is the implementation of 7 level voltage inverter. In this video we have learned about MMC's modular multilevel converters, how they work and why we use them, and at the end we have developed a strategy for the implementation of 7 level modular multilevel converter using half bridge configuration. So this was all about MMC converters. Thank you. See you again in next video.